Okay, so today we're going to look at implicit differentiation. All right. Now, up until now, we're used to seeing functions like this: y equals x squared. Okay. So in other words, y is a function of x, isn't it? Yeah. And what we say is y is given explicitly in terms of x. Okay. So in other words, we can write y equals when we've got it in terms of x. And then when you've got that, it's really easy to differentiate, okay? Because, you know, you dy dx, then you just bring the power down, don't you? And you get 2x, okay? So it's really easy to find dy dx. So when a function, okay, is expressed explicitly in terms of x, okay, what we do then is, what we say is that we're differentiating explicitly to find dy dx. And it's really easy. So if you think about these functions here, okay, these are the sort of things that we've done before, and you can easily find dy dx here because y is in terms of x. However, not all functions are given in this form where we've got y in terms of x. Y is a function of x. Sometimes we have functions such as this one here. Okay, this is an example of an implicit function. Okay, because you haven't got y equals. Okay, you've got x squared plus y squared is equal to 4. Okay. Similarly, if you go to the bottom of the page here, we've got other examples, okay, more complex other examples, where we haven't got y equals. So these are what we call implicit equations. So the question is then, well, how on earth are you meant to differentiate these? Because we want to find, don't we, dy dx. That's kind of important. If you remember, dy dx gives us the gradient function, yeah? So we can work out the gradient of the curve at any particular point. So it's important for these curves here that we're able to find the gradient function, we're able to find dy dx. So how do we go about doing it? Well, quite simply, what we do is we differentiate, okay? So for instance, this example here, we differentiate both sides with respect to x. So every term you see, you've got to differentiate it with respect to x. But of course, you're going to spot a problem on you. You're going to see, well, how can I differentiate this with respect to x? How can I differentiate this with respect to x? That would be easy, yeah? Because that just becomes 2x. But how am I going to differentiate this? What you do is when you have a y term, you simply differentiate it with respect to y. Okay, so you know that would become 3, wouldn't it? And this would become 8y. But then you have to multiply it by dy by dx. Okay? So every time you have a y function, differentiate it as normal, but you've got to multiply dy by dx at the end there, okay? I can go through why that works, okay? But essentially it's using the chain rule, okay? So today I just want you to sort of accept that that works. And whenever you see an implicit function and you're differentiating with respect to x every term, if you have a y term, just differentiate normally but plonk a dy dx at the end of it. So let me just do a couple of quick examples here to start with. So suppose I've got this here, x squared plus y squared equals 4. Okay, so quite simply then we'll differentiate, right? I'm going to write this down every time I sort of do these questions. Differentiate with respect to x, WRTX. So differentiate that becomes easy, doesn't it? Because that just becomes 2x. Differentiate this, well, yeah, it's a y term, but differentiate it normally, so you get 2y, yeah? But remember, you've got to multiply it then by dy dx, okay? So plonk a dy dx at the end. Here then you've just got 4. Well, that's a constant, isn't it? So differentiate that as well, yeah? But it becomes 0 and differentiate that. So you end up with this here, okay? And we've got an equation. And what I can do now is I can rearrange this to get dy dx equals to something, right? Perhaps one thing we could do, if you notice here, we've got a common factor of 2. So let's sort of simplify by dividing by 2 then. That might make life a bit easy for us. So if I divide this by 2, I get x. If I divide this by 2, I just get y. Dy dx equals 0. Okay. Then to get dy dx equals, I've got to take that x over the other side. Okay, so I get minus x when I take it over. And then, of course, you've just got to take that y over. Now, because you're timesing here, when you take that over, you're going to be dividing. Okay, so minus x, we've got here, take the y over, we're dividing. And there's your answer, okay? That's what dy dx is. That is the gradient function. And yeah, it's in terms of x and y, okay? That's what happens with implicit functions. we'll have our solution, our gradient function in terms of x and y. Okay, so before we go on to the exercise, maybe I'll do a second example, okay, just to give you a bit of confidence with this. So let's just take this one down here, yeah, this one we saw there, x squared plus 3y plus 4y squared minus 7 equals x. So let's try that one, shall we? So I've copied that one down now. So again, I'd say, look, differentiate, okay, with respect to x, okay, so you differentiate both sides with respect to x, each term in turn, so that becomes 2x, that's easy, and the 2 down. Now that's a y term, so you differentiate it as normal, so 3y just becomes 3, but remember to times it by a dy dx, okay. Then you have 4y squared here, okay, well, just differentiate that, yeah, so you bring the 2 down, so you get 8, so it'll be 8y, but remember, because it's a y term, you've got to times it by dy dx. Minus 7 just becomes 0, okay, disappears because it's a constant, and x becomes 1 when you differentiate it, okay. So what you've got is this then, right, and you've got a pair of terms now with dy dx, okay. Now, what you can't do is obviously put them together, because this is 3 dy dx, and that's 8y dy dx. But what we can do is factorize out the dy dx. Okay, so if I factorize out dy dx there, a bracket, what do I times by dy dx to get that? Well, it'll be 3. What do I times by dy dx to get this? Well, it'll be 8y. On the other side, then I've got 1. Take that 2x over, so it becomes minus 2x. And I think then what have I got to do to finish? To get dy dx on its own, well, I've got 1 minus 2x here, all over this then, so take this over the other side, because I'm timesing, when I take it over, I'm dividing. Okay, so hopefully that makes sense, but we are going to look at an exercise now slowly, take our time to understand it a lot better.